Well, Go seminar. We are happy. We are very happy to have Joanna Jasińska from jointly at Laurent and Renyi Institute here this week, and she will tell us something about permutation limits and some generalizations of models.
Thank you very much, Hansa, for inviting me. It's always a pleasure to be in Prague. So today I will speak about my joint work with Balázs Ráth. It's based on a project that I actually used in my master's thesis in Warsaw, and then I brought it to Hungary, and it escalated quickly because it turned out that more than one person was interested in this. So the title is a Permuton limit of a generalization of the Mallows and K-card minimum models. I think the Mallows model can be well known to many people. It's a well, okay, so apparently it's a famous model in some statistical physics that I'm absolutely not an expert there. But there is also the second model, which is not as famous. It's called K-card minimum models. And I will talk about some unexpected similarities between those models and the generalization of them. So let me start with mentioning how are we going to think about permutations. So one way of obtaining a permutation of a numbers is by sequentially picking cards from the deck. So let's say I have a deck of cards, all of them have numbers. I can choose a card in every step according to some specific rules. And this way, when I finish picking, the deck is empty. I'm getting some permutation of n numbers. And we can represent any permutation graphically. And this is, I don't know, I guess maybe people are familiar with this, but just in case, you know, I can draw a unit square. I can divide it to, let's say, 4 parts. And for example, this thing will be permutation 2, 4, 3, 1. So I will regularly think about permutation in this way, that these are just some squares in the bigger unit square. And as I mentioned before, we have those examples of random permutation models. The 2 examples that appeared in the title of my talk, the K-card minimum, it was introduced by Travers in 2015. And the more famous model, the Mallows model, it was introduced by Mallows in 1957. So let's start with making you familiar with both of those models, and then I will explain how did we decide to generalize them, how we describe the more general family of random permutations models. So what is the K-card minimum model? In this model, I have a deck of n cards, and there is a procedure to get a random permutation. The procedure is as follows. I have n numbers, and this is my D1. And then in every step, I'm picking uniformly at random K cards from the deck. And these are those, okay, the pointer, right, okay. So those CT1 up to CTK, these are the IID uniform samples from the deck at time t. And then I pick my T card as the minimum of those K numbers. And then I get the new transformed deck of cards by just removing my minimum. In this way, if I just repeat this procedure, I'm getting a permutation of n numbers. So what can we say about this model? For example, one can notice that if k is very big, for example, if k is equal, if k would be equal n, then we would be very, very close, or even exactly would get the identity permutation, because if I take k equal n, then in every step I just take the whole deck, and well, the smallest card will be always the one on the bottom. One can also notice that if I pick k equal 1, then I get just the uniform distribution on Sn, because every time I'm just picking a card at random from the deck. So this is the K-card minimum model. And then we have the Mallows model. The Mallows model, actually, I will describe a way to get a permutation in this model in this algorithmical way, so that you see the analog with the K-card minimum, but also there'll be another GCP. So start with this algorithmic way of getting the Mallows permutation. So again, as before, I have a deck of n cards, and this is my D1. And then in every step, I will be sampling cards according to some fixed distribution. This mu, it will be just a truncated geometric measure. Here is the formula for this measure. So I'm just picking the position in the deck according to this measure, and then I pick the C tilde T lowest number cards in DT. So we don't think about the numbers on the cards anymore. We think about the positions. And then, again, as before, I just remove this card from the deck. And when I'm done with the whole procedure, I'm getting a random permutation. I don't know. Do we need some time to just stare at it for the 10 seconds and see the similarity? Or I think people look happy. So that was the second model. And interestingly, I can get a Mallows permutation in another way. Namely, I don't have to be focused on picking cards sequentially. I can just think about the whole set of permutations of Sn of the group. And I can pick a permutation at random with this probability. So this is some constant Q. I will be mainly interested in Q between 0 and 1. This is this Q to the number of inversions divided by some normalizing constant to make it a valid probability measure. And it turns out that it is the same, that this previous algorithm gives us the same distribution on Sn as picking in this way. So a couple of observations about this model. For example, we can notice that if Q is in this regime that I want, that it's between 0 and 1, then this model favors permutations with smaller number of inversions. So if I have a number that is tiny, between 0 and 1, then the bigger the power, the smaller the value, right? So I don't like permutations that have a lot of inversions in this model. And when Q is very close to 0, then we are getting closer and closer to the identity permutation because we punish the inversions, right? So we prefer, when we're very close to 0, we prefer something that has almost no inversions. And again, as before, there is a special case of this model that gives us just a uniform distribution. So if Q is equal 1, then my normalizing constant is defined to be n factorial, and it just gives me the uniform measure on the group of permutations. So these were my two models. And in 2015, Travers stated a conjecture that those two models, they are similar in some sense. So what was observed, that if you pick Q to be around 1 minus k over n in the Mallows model, where k is the parameter from the KCM model, then those models have a similar band structure, and I will explain very soon what do I precisely mean by this graph, by the band structure. So if you think about a permutation as little squares in the unit square, then if you make this this picture to have a lot of tiny squares, and it turns out that the k-card minimum permutation has more or less this shape. If we have a lot of points and if we zoom out from it, and the Mallows model, we also have a lot of points somehow here. And it turns out that most of those points will be concentrated in a tube. And this tube will be the same. Of course, it will be dependent on the parameters, but if we choose the parameters properly, then it will turn out that most of the points lie in a tube around the main diagonal with this width of order 1 over 1 minus q, or n over k. So, so it was a conjecture stated in 2015. We managed to answer positively to this conjecture. It indeed works like that. And one has to mention that for the Mallows model, it was actually known. It was a known result by Batnagar and Pellet in their paper Lengths of monotone subsequences in a Mallows permutation in 2015. So it was the same year as when Travers introduced this K-card minimum model.
Yes. I have a question.
Go ahead.
If Q is roughly this 1 minus K over N, Q is somewhat getting closer and closer to 1, am I right?
I mean, if K is large, then Q is tiny, right? Because if K is big...
But K is much smaller than N, no?
I mean, you can pick a large K and then...
I mean, my trouble was that this is sort of going to the uniform case rather than the diagonal case.
But K is fixed. Like if you think about the fixed K, then no, you can like you can stay away from the uniform case, because for the uniform case, of course, like you get two identical models.
No, that's not my problem. My problem is that that type of behavior I would expect when one is getting closer and closer to the identity, which I thought means Q is getting closer and closer to 0.
Yes.
Q is getting closer to 0.
It's fixed and it's going to.
If K is fixed and is going to infinity, then that's Q tends to 1, not to 0.
Okay, give me a second. I'm a bit confused as well. I mean, I know that definitely the choice of the parameters should be like that. I'm just, at this moment when, you know what, we will get to the pictures then with the simulations, and I will come back.
Okay, I mean, it was just that if I'm doing something wrong in my...
Yeah, that's true. So, okay, so let me just, we will come back to this with the simulations, but let me just state myself in this way that for the appropriate choice of parameters, those models behave as they should. Yeah, but let's discuss it with the pictures. Okay, so these are the pictures, and you can see that you have a very big deck of cards. So you have n equal 10 to the 4th power, and k is equal 20, and then the k card minimum permutation looks as follows. And if you take a Mallows model on the same size of the deck of cards, so 10 to the 4th, and Q of this form E2 minus beta over n, where beta is 20, then you get this picture. So wait a second.
So it seems like that Q is getting to 0. So.
It seems like Q is getting to 0. So
maybe if you remove this 1 minus, make it. It will keep it.
Yeah, maybe there's a typo in this. It looks like that. Yes, you are completely right. Sorry for this issue, because at least with the simulation it works, right? Like you can see that that Q is getting, indeed, as you say, it's getting to 0, and the band structure works as it should.
So shouldn't it be like exponential or a over n?
Oh, so it's getting to 1, yeah.
Okay, now I was confused. Wait, because E2 minus beta over n, like beta is close to 0, so then E2 minus this thing is close to 1.
Yes.
Amazing. Okay.
But then it's uniform, which I have no. Okay, it's maybe just my digestive system.
Maybe it's, yeah, I'm not fully understand your digestive system. Like, what's it?
I thought that tending to 1 is sort of bringing me closer and closer to uniform permutation.
But when Q is tiny, that's like for sure. When Q is like a very, very small number, then the more inversions you get, the more annoying it becomes. So right?
Well, the second point is when Q is equal to 1, we draw them uniformly.
So if you are close to 1, I kind of say, qualitative way, we should be close to uniform.
But no. Like okay, but there is a difference. Like you draw permutations uniformly, so like all of them have equal probabilities. And here, in this case, when you are close to 0, then you favor the identity permutation. So like there's like two opposites.
That I understand.
Good.
But those pictures were okay. maybe is that picture close to identity or is it close to uniform? As a picture.
Well, as a picture,
I thought it's close to identity. I will review my choice. But maybe that's where my intuition.
I think it's wrong. No, they are not close to. No, they are not close to the identity because look, like the points are like widely spread on the bottom, right? So if you were close to the identity, that would be like very much concentrated around the diagonal. No,
But it is on the other side.
It felt to me it is, but maybe
at the end,
that was the wrong feeling.
Wait a second. Like at the end of the K-card minimum permutation algorithm, you need to be close to the diagonal because like the deck is smaller and smaller, right? So you are more likely to choose smaller cards at the end, and then when the deck is very small, then you get closer. So of course the shape changes, but like at the very end, it's like it's widely spread. So I wouldn't say that this is close to identity.
Okay.
Anyway, so I don't know, like, is this more or less a bit more clear or?
No, but I'm happy to live with that.
Okay, so let's just continue and then we continue after the presentation. Okay, so what we did with those two models was introducing a model that generalizes the KTM and the Mallows model, because we noticed that, okay, actually in both of those models, it's about specifying some distribution of this leftover deck of cards. So every time I'm picking my card from the set of cards that are left in the deck, and we have some distribution in the KCM model, we have some specific distribution in the Mallows model, and let's just say that, okay, now on this leftover deck, I'm fixing some distribution and I do the same as before. And this gives us the whole family of random models. And we proved that the sequence of random permutations in this general model, it converges to a deterministic limit. I will explain very soon what do I understand by the limit of random permutations. As a consequence of this, we got the weak law of large numbers for pattern densities. I will also explain what do I mean by the density of a pattern in a permutation. And we also proved this conjecture of Travers that if we take some assumptions on the parameters that those models have, then the general model exhibits a certain band structure around the diagonal. So it actually works this way for all of those models in this family. So in particular, also for Mallows and KCM. So how do I define this general model formally? Now I'm fixing, strictly dictating continuously differentiable function g with some boundary condition. It's 1 at 0 and 0 at 1. And then for each n and each element of the set of numbers from 1 to n, I define some probability distributions supported on n minus I minus 1 cards, because that's how many cards I have after I steps of my procedure. And it's just a formula. I'm just drawing the cards with this kind of distribution, and this is basically what I have just said. So this is an algorithm that shows you that okay, actually the two previous models are special cases. You can see the analogy. Again, I have a deck of n cards, and in every step from 1 to n minus 1, I sample C tilde, which is the position in the leftover deck, according to this distribution that I specified in the definition of the model, and I take CT to be the CT tilde lowest numbered card in my deck. I remove this card, and this way I receive a permutation. So you can see that if you pick g of this form, 1 minus x to the k, or this more complicated formula with the exponent, then respectively you receive either KCM model or the Mallows model. So they are the special cases of this general thing with appropriately chosen chosen G. So now let's take a deep breath and let's go through the theory of those Permuton unities. So as I mentioned before, we can think about any permutation as of a cloud of points if the unit is square, and I can associate some probability measure with any picture like that. So I just put the mass 1 over n in every such a square. It gives me some measure, and I can study the global geometry by just taking a limit of the sequence of measures that I'm getting through like seeing my sequence of permutations of those unit squares. So this is a bit like with graphons, right? This is like the same idea. And the limit of the sequence of measures, it just gives me the macroscopic shape of a permutation. So if I take very big decks of cards and I zoom out, then this limiting measure, it tells me how huge permutations look like from the distance. So the definition of a permuton, it was introduced in the paper Limits of Permutation Sequences by Hoppen, Kohayakawa, Moreira, Ráth, and Sampaio. And so the formal definition of a permuton is that this is just a probability measure of the unit square such that both marginal distributions are uniform on 0, 1. I don't know, are people familiar with permutons here? I have. Okay, so I should continue with this. Okay, I just didn't know what to expect, but it's fine. So if we have a random vector xy distributed according to this probability measure on the unit square, then of course I can think about the joint cumulative distribution function of this vector, and I'm just counting how many points fall to a rectangle. So maybe I will draw another picture for this. No, that's not what I want. Is there a proper sponge for the board?
What you just held was a sponge.
Sorry?
It might be behind this.
What you just held.
No, there is. That is broken one. That's okay.
You lift the whiteboard up. You lift the whiteboard up.
Okay.
Isn't there a sponge? Yeah, that's what I think.
Oh,
It's slightly better than the
breaking.
Yeah, I mean it will disappear from the camera, but to be honest, thank you so much. Anyway, so coming back to the definition of a permuton, it's just about sampling points from this measure, and I can always I say that this function f will be just the number of points that I sampled in such a rectangle. And for technical details, we were using something that we called cup CDF. So it wasn't a rectangle, but it was this L-shaped area, and we were just counting the points that fall into this L-shaped area. I only tell this for technical reasons because it will come up later. But yeah, so okay, so the definition is just that we think of probability measures on unit squares. So if I have a permutation, I can associate a permuton with my permutation in a natural way. So as I mentioned before, we can think of a permutation as of little squares in a bigger unit square, and the joint PDF of a permuton associated with this permutation will be just putting the mass n on every such a unit square, and then we are not continuous anymore. We are now counting. We now have those like we don't have points. We have squares, and now by a joint CDF in this discrete version, I will denote just again counting the numbers, like how many times I was below the level j and before some time t. So f is basically the math of the little squares inside the rectangle again, and the cup CDF V is defined analogously to the one in the continuous version. And okay, the important notion in this whole theory of permutons are pattern densities that I mentioned earlier. So, okay, there's maybe a lot of formalities, so it would take a while to parse it, but the density of a pattern in a permutation will be just the ratio of the number of occurrences of a pattern inside a permutation. So let's maybe give an example rather than go through complicated formulas. If I have a permutation of this form, 1, 2, 3, 4, 5, 6, and let's say it looks like that. Let's say it looks like that. Then I can think, for example, of inversions. So any two squares that are in the order that is indicated by this permutation, which is the representation of the inversion, any points in this order are the occurrence of this pattern in the bigger permutations. For example, those two guys give me an inversion, but also this guy and this guy, they also give me an inversion. And if I count all of the occurrences of this pattern and divide it by the total number of tuples of the length of this pattern, then this is naturally the density of a permutation, of some permutation that is my pattern in a bigger permutation. So yeah, as I mentioned, the example with the inversions, the density of inversions is just the number of occurrences of such a pattern in a bigger permutation divided by n choose 2. It's always a number between 0 and 1. And one other technical thingy that I want to mention before moving further to my results are the so-called mu random permutations. So, so before I explained how to receive a permuton from a permutation, and now I want to explain it the other way around. So now I have a permuton, a limit permutation, a permuton mu, and I can generate the new random permutation just by drawing points at random from a square. So so basically, let's say that I'm drawing points according to this limit permutation mu. I'm getting such a picture, and I can associate the permutation of this picture. I can say that, okay, let me just divide it like that. And, you know, those points, the relative order of them will give me a permutation if I just put squares here. So the formal definition of this, so that's the intuitive way of thinking about it. The formal definition is that I draw points uniformly from 0, 1. Then conditional on them, I generate the y coordinates. I put them in order, and the new random permutation is given by sigma of I equals j. Basically, if and only if xi star and yj star, so the elements of those ordered tuples, they give me a point. So I think this is a terrible way of speaking about it. I really, yes. I really felt a lot of relief when I realized that, okay, this is basically the same as thinking about it this way, that you just sample points and the relative order of those points, it gives you a permutation. So let's maybe remember this less formal way of speaking about it. And if I have a permuton, as I said, I can associate a permutation with this permuton, and I can think about the density of a pattern in the permuton. And by this density in the permuton, I will just understand the probability that a mu random permutation is equal to this pattern. So again, I had the density of a pattern in a permutation and the density of a pattern in a permuton. And one would think that why shouldn't it be the same? But actually, it's not. It's a good it's a good exercise to think of. Or I don't know. I can also explain with an example maybe after the talk. There is a very simple example for this. But what we should remember about it is that those quantities are close. So if I have a pattern of length k, then the density of this pattern in the permutation will be not much different from the density of this pattern in the permuton. The difference of those two values will be bounded by k choose 2 over n. So this is almost everything from the theory that we need to know. We are getting there. Let me just also mention what do I understand by convergence to a permuton so that I can then explain our main and most important result. So I have a sequence of permutations, and what does it mean that the sequence converges to a limit? Namely, I take a sequence of permutons that the ith element of the sequence is associated to the ith permutation, and I take mu, some permuton, and I say that mu n converges to mu if a sequence of random variables distributed according to mu n converges in distribution to the pair of random variables distributed from mu. So this is all about convergence in distribution. And in particular, it means that the cumulative distribution functions converge pointwise. And the reason why I spoke so much about the pattern densities is that the equivalent condition of the convergence is that the sequence, like for every fixed pattern, the sequence of densities of the pattern in the permuton converges to the density of this pattern in the limit. So it's exactly like with graphons. Just now we have permutations on graphs, but it's the same idea. Okay, so that was the end of the theoretical part, and we are happy to come back to. And do I still have my time?
15 minutes.
Okay, I'll make it. Yeah, but okay, let's not be very quick because that's the more pretty part of the talk. So coming back to the G-random permutations, to our general model, let me just quickly recall that we had some function g, it satisfied some assumptions, and according to this function g, I was drawing cards from the deck. And Mallows and KCM were special cases of this procedure. So now we introduced permutons as a language to describe the global shape of permutations, and we want to apply this framework to our model. And the way we do it is that we kind of guessed, let's say, we recognized what should be the limit, and then we proved the convergence to this limit. Let's say that again I have this function g, it satisfies my assumptions of the general model, and by Vg I denote the unique solution of this differential equation, the initial value problem. Let me just remind you, just to at least try to keep everybody on the same page. The Vg, it was this L-shaped dot that, okay, I had a measure mu, and I was sampling points according to this measure, and Vg, it counts how many points fall into this area. Okay, so that was Vg, the mass in this L-shaped area between y and x. So yeah, we guessed what the limit should look like. I will explain how did we manage to guess what it should be. And it is just the solution of this differential equation. It can be solved explicitly. The solution looks as follows. This is there is some function u dependent only on this function g from our family, And Vg is u2 minus 1 of u of x plus u of y. It's a very pretty solution. And one can show that our assumptions on G imply that this Vg can be continuously extended to the whole unit square. So there are no issues with continuity or whatever. And it's a valid Permuton limit. This can be also checked that it actually satisfies this definition. And the theorem that we proved was that if we have this fixed function G satisfying the assumptions of our general model, and we have a sequence of G random permutations from this general family, then the cumulative distribution functions of the permutons associated with our permutations, they converge to this cumulative distribution function of this previously identified limit. So we have the convergence in probability. And in the case of the Mallows model, the limiting Permuton is as follows. Sometimes we talk about V, sometimes we talk about F, but the relation is, it's very simple. So F, it was just the mass in such a rectangle. So you can see that passing from this to this is the same, is quite simple. So if we have V, this cup CDF, we can easily recover the formula for F. But anyway, in the case of Mallows model, the limiting Permuton is this beautiful formula with a lot of exponents. And in the case of the KTM model, the limiting Permuton is here. It's a bit more user-friendly, I would say. But anyway, what is nice about the solutions is that they are explicit. Like we have the formulas. So as I should say, the result about the KCM model is new. We proved it with Balázs, but in the case of the Mallows model, this result has been known previously. Interestingly, for the Mallows model, it has been known before they even invented permutons, because the first paper about permutons, it was 2013, as far as I remember, or 15, not such a long time ago anyway, and the result about the Mallows model and its limits, it was proven by Starr in 2009, and he was talking about thermodynamical limits. So it was a paper with a lot of differential equations, and it was there was a lot of thermodynamical things there. So it was a bit different framework than in this paper about the permutons, but the idea essentially has the same root. So how do we prove this? That's the most fun part. So our method was to notice that if we fix the J, then this process V sigma n, so the long sequence of my L-shaped regimes, this is a Markov chain. And we know the formula for the conditional increment of this Markov chain. It has an explicit drift, the expected value of the difference between two consecutive steps, given that we know the past, can be expressed by an explicit formula dependent only on the function G, on the parameter of this model. And look, the differential equation that I mentioned before, it looks kind of similar, right? It has a very similar form. So this drift above, this formula here, this is just the discretization of this differential equation, and just to the fluctuations of the difference of them rescaled, we applied the Doob decomposition. So we represented this as a martingale plus some predictable process. We bounded both parts separately, and as a conclusion to that, we received the convergence in probability for the cup CDFs. So as I mentioned before, one can pass from the cup CDF to the usual normal CDF that we like from the probability classes. And it implies the convergence of the pointwise convergence of the CDFs. So it implies convergence to the Permuton limit. And one important remark is that, I mean, okay, maybe it's not very important, but it's at least visually pretty, was that when you study this K-card minimum model, you can convince yourself quite easily that this is true in this model, that you wonder what is the probability that the I card is equal to J, then you can notice that this is exactly the same as the probability that the J card is equal to I. So as a master's student, I discovered this about this model, and I had no clue how to prove this. But then it turned out that actually for the KCM, it's not so difficult to prove this, but we can also, using the result about the Permuton limit of the general model, we can prove that actually for the general model, the CDF is a symmetric function. So so it's not true only for the KCM, but for all of the models in this family, that they are very symmetric. And as a corollary, as I mentioned before, being convergent to a permuton implies that the sequence of the densities of patterns in the permutations also converge. So we also received this little corollary that if I fixed pattern of length k, then okay, actually this p shouldn't be there. Sorry, this is a typo. This is just convergence. Convergence of the sequence of the densities of this fixed pattern in my sequence of permutations to the density of this pattern in the Permuton limit. And this is nothing new. It just follows from this previously established Permuton result in this initial paper about permutons written by 5 authors. So one more important thing that I do not dare to say in very specific details because there is a lot of technical things there, but I'm happy to explain it at least briefly, that, what happened with this concentration around the diagonal that I promised at the beginning. So the technical part is that we have to describe some scaling function. We have our general model, we have the function g associated with this model. And let me just define this function gamma to be some kind of scaling function. I will explain later why do we need it. And for each alpha, I also describe this psi alpha of s using this formula that you can see here. We take some assumptions on those functions. How do we use them? So I define two random variables, u and v. They tell me more or less how how the points from my permutation behave around the diagonal. Okay, so one of them is just the mean, and another one is the difference rescaled a little bit. And it turns out that those two random variables, they converge in distribution. So again, this x alpha, y alpha, these are just points from my drawn from my permuton. It turns out that they converge in distribution to a vector of two random variables. One of them is uniform, another one is a rescaled logistic distribution. And how should I think about this theorem? So if the parameter alpha is large, then I know that the mass of the distribution of those points will be mostly concentrated in a thin tube of some thin tube around the diagonal with explicitly specified width. It will be proportional to 1 over gamma of alpha, which was the scaling function that I mentioned on my long slide with assumptions. And the reciprocal of this C of u, it describes to me how the local width changes. So you will see on those pictures that, for example, for the KCM model, those scaling parameters, they are expressed explicitly by those formulas. And look, let's meditate over it for a while. This is my plot of points from the KCM model. I can see that they are mostly concentrated in some kind of tube around the diagonal, but I also can see that the shape changes. So this is described by this function psi. So I mentioned in the statement of this theorem that the local width changes like the reciprocal or inverse, rather 1 over psi. And you can see that if S is close to 1, then the width will be smaller because we are going to 0, and you can see that here the tube should be getting smaller and smaller, and at the very beginning it's wide. And for the Mallows model, this scaling function gamma is just equal to alpha. Psi of S is equal to 1, and the psi of S is maybe like more interesting now because you can see that it was supposed to describe the local width, and in the case of the Mallows model, it goes uniformly. So we are on a stripe. Again, the main conclusion from this theorem is that most of the points are locked between stripes of certain width, and we also have some additional knowledge about the shape of those points inside the tube. So that was pretty much this. We can come back to the discussion about the parameter now, and I will realize if I made a typo or not.
First things first, let's have
Thank you so much.
Meanwhile, I've realized how much I underappreciated the exponential shape in this Mallows model. So everything you said was correct, and I was just.
Could you explain to me why was it?
Because I mean,
back to this because I think I didn't fully understand.
I mean, something maybe tends to 1, but much slower with respect to the exponential.
So was it about being, I don't know, confused about those pictures?
No, I mean, I was confused that if this Q is getting to 1 somehow for this Mallows model, I would sort of start expecting uniformity.
Yes.
And I was not seeing this uniformity, I was rather seeing this stripe, but it's not, I mean, it's getting to 1, but not that fast with respect to the exponential model. So I'm not sure about you, but I am happy. As a matter of fact, I'm so happy that I don't want to think about this any further. But
they show it too, but like it's only set at it's equal to 1.
No, yeah.
But then it's 0.999.
But this is, I mean, it's more than 0.999, but it's less than to compensate the exponential growth in the model.
Yeah, so maybe if you put the previous slide even further. So here, this one. So there's like, if Q goes to 0, then we are getting to identity, and then there is, if Q is equal to 1.
Yeah, but I mean, I would somewhat expect some continuity. I mean, I agree it's not written when Q tends to 1. You get closer, but I mean, it's continuous process with respect to Q.
Yes.
So
let me have a different question. So when looking at the shapes, it seems like obvious that the K-card model is like an arrow that is closer and closer to the diagonal. And I think that this is caused because the number of cards that we draw starts being closer and closer to the size of the permutation or that we are picking from.
Yes.
So would it be natural to pick always the same fraction of cards from the deck and taking the minimum from them instead of taking the same number of cards? Would that then make a shape that would be even closer to the Mallows model?
I mean, that would give another model, that's for sure. I think the right question to ask is that okay, can I describe an algorithm that gives the same kind of algorithm that is here? Because the whole magic with this G-random model is that I can always represent it as the algorithm of drawing from the leftover deck. So you say, okay, let's just take a fraction, a fixed fraction. So it will give us some function. So let me think about it. We will be closer to the Mallows model. I mean, intuitively, I would say that yes, but yeah, just that's the first instinct, let's say, because indeed, like we can represent it as the algorithm, right? So it's the same way as previously. So I would say yes. It's it's a bit different than this KCM, but it's just one of the many models in this family.
Okay, yeah, I felt like some of the motivation was just to like get again the Mallows model, but it's a different definition, like just picking some cards and take the minimum. Then yeah, wondering whether this would be this way we would get something that is even closer to the
Okay, it's something to think about.
I have a question, unrelated with that. Like if you maybe if you move to the slide with the map and the one about the tools like this map, this.
That's yes.
Uh,
That was a cool idea. Let me find it.
Yes. So that really reminds me like this differential equation method coming from Wormald, and at least some people in probabilistic combinatorics are of using the technique. Have you? I mean,
the techniques were known. That's clear.
So I mean, have you tried? So they have lots of black box type big result, like heavy results that you can just feed instance in, and it will. From my user point of view, it will do the decomposition and the prediction for you, and you just get out the convergence for just quoting the theorem. Have you tried to see?
I don't know this paper, so
okay.
I'm not sure.
I mean, it's also it's a general result, so it has a couple of assumptions, and not all these assumptions might be needed, might be fulfilled by your particular setting. So, I'm not saying that like one can always black box.
I'm happy to see this paper. I hope it will not destroy the result. But...
No, I give it this. I know. Okay, I'm happy to show you the. Yep.
Can I quickly go back to the pictures? And so if I understand it correctly, then Mallows model will try to get the permutation, will prefer permutations that are inside of the tube, but it may happen that there is a permutation that fits precisely into this tube, but it's very, very unlikely that Mallows generated. Yeah.
Most of the points are there, like with high probability, all of the points are inside.
1 second.
So the meaning of being inside this tube is that with high probability most of the points will be inside.
Yeah, but not the other permutation. That the Mallows just generates inside of the tube, but if I'm inside of the tube, that Mallows does not generate it, and the general model has this same property.
Yes, exactly. Yes.
Okay. There are no more questions. Thank you, Joanna, again for your talk.